next, we will move to week 10. Week 10 of Factor Auto-Regression Models. Factor Auto-Regression Models. Lecture note 10-15. Okay, we will discuss this one. So this is it. Okay. Uh, yes. So factor autoregression time series. So this is a factor autoregression model. So we deal with vector. So this is a vector xt. This is a column vector x1t and x2t column vector with two elements. And we have data vector of data. Okay. Time series of vector data. So that it is x1, x2, and up to xt. So example. Okay. Joint time series of US quarterly GDP and unemployment rate series, or the daily closing prices of oil related ETF like oil service holdings and energy select section like Spider XLE, and for more than two series. Okay, but we have only two series here. Possibly this factor X could be longer, or quarterly GDP growth rates of Canada, United States, United Kingdom, and United States. So it is trivariate series. So then question is, okay, well, instead of individually estimating this one and this one, why we want to estimate x1 and xt together? Why? A. Obtain the relationship between the series, and B. Improve accuracy of forecast because we use more information between the two series. See figure 1 for log price to energy fund. The price seems to move in unison. So if we see figure 1, yeah, figure 1, two series, they seems to move together. So, well, this first time series may contain information for the second, and the second time series may contain the information about the first. So it is maybe more efficient to estimate, to analyze both time series together. Okay. Some background: weak stationarity, both. Okay, so ext, so unconditional expectation of this factor is mu, this is also vector, and covariance matrix, it is time invariant unconditionally. If it is time variant, it is not weakly stationary. Okay, so, well, because this distribution does not change, therefore by sampling the data we can estimate the distribution of the data. Okay, auto covariance matrix. Okay, this is important concept. When we analyze time series, vector of time series, okay, then we time series vector, auto covariance matrix always happens. So this is basically analogous to autocorrelation. So B capital gamma L is ext minus mu and xt minus L minus mu prime. Okay, we transpose. So what is this? Then this is this 2 by 2 matrix x1t, x1t minus 1, x2t, x1t minus 1, now x1t, x2t minus L, and then xt, x2, xt x2 t minus L. So it is very gamma 1 1, gamma 1 2, gamma 2 1, gamma 2 2. So basically it is not symmetric unless L is 0. Then in general this and this are not same in general. Okay, so gamma 1 2 rec 1 is covariance of x1 t and x2 t minus 1. So x1 t possibly depends on past x2 t. Now capital gamma 2 1 with one leg is covariance x2 t and x1 t minus 1. x2 t depends on past x1 t. Now we can see some diagonal matrix. D diagonal means off diagonal terms are 0. Let's say D is standard deviation x1t and x2t. So then diagonal matrix basically capital gamma with leg 0 and then with square root and square root of gamma 2 to 0. Now we can see the cross correlation matrix. Cross correlation matrix. Cross correlation matrix rho L is the inverse gamma L the inverse. Okay, this is cross correlation matrix. So by in some sense, this gamma, okay, this gamma L is D rho LD. Okay, we multiply D each side. Okay, thus rho IL is cross-sectional correlation between XIT and XJT minus L. From the stationary condition, okay, gamma L should equals gamma prime minus L and rho L should equal to rho prime minus L. For instance, correlation 1t x to t1 should be same to correlation 2t and x1 t plus 1. Okay, there is only it doesn't depend on time. Okay, that's the dependent is the definition of weak stationarity. So basically we ignore t, only gap between the time matter. Okay, and the which one comes first. So in both cases x1 comes first and the time gap between x1 and x2 is 1. Now testing for serial correlation. Now we can undertake multivariate version of Hyoung-Goo box QM statistics, which is available. So in the null hypothesis, rho 1 up to rho m is all 0 versus any one of them is not 0. The test statistics Q2m looks like this. Okay, looks like this. Which follows chi-square distribution with degree of k square m. Okay, note TR is sum of diagonal element. Okay, remark: analysis of multiple time series can be carried out in R via package MTS. Okay, so we can skip R demonstration. You can do it at home. Now, factor autoregressive model. Okay, factor autoregressive model VAR. Now VAR1 model for two return series. Okay, so R1T, R2T, and something like this. Okay, so yeah, they are cross correlation clearly. Cross correlation because this phi 1 2 and this one because they are not 0. This is not 0. This is not 0, and this is not 0. Okay, therefore, well, they interact each other. Okay, where AT, A1T, A2T sequence IID independently, identically distributed by variate, normal, random variable with mean 0 and covariance matrix. Okay, so rewrite model as we can write this one. Okay, this way. They are identical expression. Where phi 1 denotes the dependence of R1t on past returns of R1t minus 1, R2t minus 1 respectively. Now unidirectional dependency. For the VAR1 model, if phi 1 2 is 0, but phi 2 1 is not 0. So here, suppose suppose this is 0, but suppose this is not 0. Oops, this is not 0. This is not 0. Then clearly, this series, first series affects second, but second doesn't affect first, right? That's what it says. Okay. Here, R1t does not depend on R2t minus 1, but R2t depends on R1t minus 1. Implying that this implies knowing R1t minus 1 is helpful in predicting R2t, but R2t minus 1 is not helpful in forecasting R1t. Here, R1t is input and R2t is the output variable, right? Because of this one. Okay. This is example of a grandeur causality relation. Grandeur causality. Okay. Second, okay. So R1T grand cause R2T. Now if sigma 1 to covariance between first time series and 0, then R1T and R2 are not concurrently correlated. Okay, correlated. Even though they are not concurrently correlated, if there is a like relationship like this, then there is a grand causality relation. Okay, right? Well, it is because not concurrent, both of them are t, but now we have a t minus 1 here, right? Now we have a stationarity condition. Now generalization of one-dimensional case. Write VAR1 model as RT 50. Now big phi RT minus AT. RT is stationary if zeros of polynomial are all greater than 1 in modulus. Equivalently, if solution I are all greater than 1 in modulus. Okay, we learned something similar in the previous univariate process. Right? So if zeros of the polynomial are all greater than 1 in modulus, so all solution of this one make 0 are all greater than in modulus. Okay, they are same. Now mean of RT satisfies this one. Okay, I pi mu 0, so mu is I minus pi inverse phi 0 if the inverse exists. Now covariance matrix of VR1 model is, of course, it looks like this. Okay, we can, well, using this one, we can easily check it from I to its inverse infinity. So that phi L is basically gamma L is pi gamma L minus 1. Okay, so this is the definition of, you can check it from the definition of auto covariance matrix. Okay, and then can be generalized to higher order model. Now building bar model, factor orderless model, order selection, we can use AIC or BIC, either similar before, or stepwise chi-square test for its test var 1 or var 2. Estimation, next, use ordinary least square method. Model checking, similar to univariate test, and forecasting is again similar to univariate case. Some AR models are sufficient to model SL returns. Program note, command var modeling, var order, computer variance information crisis for factor time series, and var estimated var model is all about R. Left var is refined as var model by fixing insignificant estimates to 0. Okay, MTS tag is model checking, and var predict the fitted var model. Okay, I think we can do some exercise before we move to co-integration. So, well, now up till now we use ChatGPT, but here now let's use uh in this case let's use oops uh yes somehow what is going on. Okay, again Claude, let's go Claude. Okay, so let's try it. Generate VAR1 factor auto regression, not generate, simulate. Okay, simulate factor auto regression process and visualize it. Use Python. Okay, we will see. Okay, ChatGPT was great. How about Claude? Claude is also very nice. Okay, so well, it generates something. Okay, A matrix, and then covariance matrix. Good. Okay, okay. Covariance matrix. Okay, copy, and then we do collab research google.com slash hashtag create equals new. Huh. Again, collab and the hashtag, yeah, create new. Oh, sign in. I have to sign it. So, okay, I signed it, and then paste the code and let's run. Okay, it takes some time. Nice. Okay. Well, yeah, let's see line by line. Import numpy s and p. Okay, import matplotlib pipeline as plt, and from stat model time series analysis API import var. Okay, from stat models time series analysis and ARIMA process import ARIMA generate sample. Okay, set random seed for reproducibility. So let's set random seed 42. Now we are one parameter. Okay, let's say number of observation 10, number of variance is number of variable is 2. Okay, so it's a bivariate process, and define the coefficient matrix of A. So this is coefficient, and define covariance matrix of errors. Okay, so this is covariance matrix. Okay, well, this time series, it seems that doesn't have a constant term. Okay, so let's generalize. Okay, here it is nice, but I want the time series var process. I want the simulated var process uh, to have constant term, constant term, which should be vector. Save the simulated data into as Excel file. Next, and then visualize simulated data with separate figures. Next, upload the simulated Excel file, and then estimate the var. Okay, let's do this way. Wow, this is pretty quick, isn't it? Pretty quick. Okay. Okay, let's see. Let's copy, and then let's go to again, and then let's delete this one and add a code. Okay, now let's run. Okay, okay, it works nice. Okay, it works nice. Okay, so let's take a look at line by line. So pandas PD random seed 42, and again number of observation is 1000. Let's make it 1000, and then number of variables is 2. Okay, so coefficient matrix A. Okay, so this one. So well, because this 0.1 and minus 0.2, so well, that's why they are two series are related to each other. Related to each other. So for example, if this is 0, if this is 0, then the second process does not grant code A, but first process grants code second process because of this one. Okay, if this is the case. Now both of them are not 0, so both grant code each other. Now we add constant term here. Okay, so here, what we are week 10, week 10 VAR, week 10 save it. Okay, week 10 VAR. Okay, and then covariance matrix is 1. Let's make it 2, and then second is 1. Okay, and then where covariance matrix, this one covariance 0 for where they should be symmetric. Okay, 2 1. Okay, symmetric. Now errors. Okay, random variable. Okay, errors is generate errors, np random multivariate normal, mean np0 number of variable, and covariance matrix and size. Okay, we use this covariance matrix, and size is number of observation. Okay, covariance matrix between the errors. Okay, so we generate errors, and the initialize time series. Time series is we have 1000 observation, 2 variable. We fill all into the 0, and then generate VR1 process with constant term. So for t range 1 to 1000, which is number of observation, time series t is c. Constant c is the constant term over here. Okay, some constant term plus a. This is a matrix algebra. A ts t minus 1 and errors t. Okay, errors t. And then generate data frame and save the Excel file. df pd data frame column variable 1 variable 2, and then, well, yes, we have a far simulated Excel file over here. Okay, and then df to Excel. Okay, file simulated Excel. So we save simulated data into Excel file where we remove index, and then print data saved to far simulated XLS. Okay, and then visualize simulated data with separate figures. So figure, we need 2 figure. Okay, so first one is variable 1, second one is variable 2, something like that. Okay, grid. Okay, we have grid true. PLT title layout. Okay, and PLT show. Load the. Okay, so until now up to process, so we generate figures. Okay, we have 2 figures. This one figure 1. Okay, first variable and second variable. And then next. Now we upload the saved data. So now we want to load this data. Okay, load this data. PDD read Excel for simulation XLSX. And now we want to estimate far model. This is simple model for loaded DF. Okay, we simply input the data and result model fit 1. Well, we assume it is far 1 model, and then print model summary. Okay, and then model summary is like this. So let's check our estimation result. Okay, result is first result of equation variable 1. Factorial constant term is, well, constant term is what is constant term? Okay, constant term was, okay, constant term was 1 and minus 0.5. Okay, 1 and minus 0.5. So constant point, it is close to 1, and then second one, this is close to minus 0.5. Okay, now for the first variable, it is itself affected by 0.5 and 0.1, and second one is minus 0.2, and then, well, 0.28. Okay, so this means, okay, we can check the correct one is correct aim is 2 0.5 0.51. Okay, so it is similar to yeah, it is, well, data is small, so it is not exactly estimated. Okay, but yeah, not exactly estimated, but if we increase number of data, they should be, well, should capture the original data better. correlation matrix is quite good. Yeah, quite similar to 0.5. Let's simulate more data. Okay, and then see whether this one, well, it of course will take more time, but let's see. More time, and then it should estimate 0.51 minus 2 0.3 better. Okay, we have more dense data. Okay, so let's see. Right, it's now similar. 0.5 0.1 0.2 0.3. So we have more data. If we use more data, then, well, we have better estimate. What if, okay, let's save time. So let me reduce data, and then what if we use fit the model with VR2 model. Okay, so okay, this is one. And what if we estimate model with VR2? Okay, then here code where the true model is VR1, but let me try VR2. Okay, with second order. Then, yeah, with lag 1, well, they are, well, this one is 5 0.5 0.1, very similar constant capture. And second one is t steady is, well, we can t steady, it is, well, it is less than 2. Okay, so it is statistically not significant. Second leg L2. Okay, how about second variable L2? Again, both of them are insignificant. Okay, again, now correlation matrix slightly decreases because the second leg captures something, but, well, this time series model seems looking quite well. Okay, now let's move to the yes, co-integration. Co-integration is very important concept, important technique in financial econometrics. So co-integration basic idea is that x1t and x2t are unit root non-stationary. Wow, what does that mean? Unit root non-stationary. Okay, which means that there is a linear combination. A linear combination of x1t and x2t is uniroot stationary. Uniroot stationary. That is, x1t, x2t share a single uniroot. That is important. There is a single unit. There is a common factor that drive both x1t and x2t. Single uniroot. And that common factor single uniroot. Why is it of interest? Stationary series is mean leveling. Now, long-term forecast the linear combination converts to a mean value, implying that the long-term forecast of x1 and x2 must be linearly related. This mean leveling process has many applications. For instance, pair trading in finance. Okay, pair trading in finance. Suppose x1t is SK Hynix, x2t is Samsung Electronics. They are likely to share some common factor, which is semiconductor performance, right? Something like that. So if we can capture that common trend by measuring the gap between x1t and x2t, well, we can check which one is overpriced over what. Okay, relative over or underpricing between SK Hynix and Samsung Electronics. This suggests trading opportunity. Okay, so example, consider exchange traded fund ETF US real estate. We focus on iShare Dow Jones, IYR, ticker is IYR, and Vanguard REIT index VNQ from October 24 and 28. The daily adjusted price of the two funds are shown in figure 2. Okay, figure 2. Okay, so they move quite together. No wonder both of them captures U.S. real estate market. So they are tightly related to each other. It's not correlation. They show common factor. This is typical classic co-integration. What can be said about the two prices? Is there any arbitrary opportunity between the two funds? Yes, possible if one deviates the other significantly. The two series all have a unit root based on ADF test. Okay, are they co-integrated? It's simply unit root because they are drifting unit root. Okay, but they are simply correlated. Trees that all have unit-based ADFs. Are they co-integrated? Now, co-integration. There are several tests that are available for co-integration. Okay, such as Johansen's test. Basic idea. Okay, consider a univariate AR2 model xt equal phi1 xt minus and phi2 x2 minus 2 and at. Okay, let delta xt is xt minus 1. Okay, now subtract xt minus from both sides and rearrange terms. Then change of xt, delta xt is gamma xt minus 1, and then plus phi 1 star. Change of xt minus 1 plus at. We can rewrite this one. Okay, we use this one because x itself is again is possibly not stable. Possibly they have a unit root. Therefore, just in case we subtract it to make it series more stable. Okay, then we do the test like this, where phi 1 times minus phi 2 and gamma is gamma phi 2 phi 1 minus 1. Okay, now x is unit root non-stationary if and only if gamma is 0. Okay, only when this is 0 it is non-stationary. It is unit root non-stationary. Okay, which means that which what does that mean? Xt is xt minus 1 plus xt minus 2, right? Testing that xt has a unit root is equivalent to testing gamma 0 in the above model. The idea applies to general ARP model. Okay, turn to ARP case. The original model looks like this. Okay, xt is p1 all vectors and matrix. Now let's say yt is a change of xt minus 1. Subtracting xt minus on both sides and regrouping the coefficient matrix, we can rewrite the model as this one. xt is this one, this phi x t minus 1, and then this term. Actually, this one is important, this one. Okay, where this one is minus this one. Okay, this is actually gamma, this is big pi. Okay, and then this one. Okay, this is called error correction model. Okay, because well yt is dependent on this one, so we correct errors like this one. Okay, we explicitly model the change of xt with x level of x, so we are error correction. Okay, important message, the matrix gamma is zero matrix if there is no correlation. Okay, if there is no correlation, this is 0. The key concept related to pair trace that yt is related to gamma xt minus, right? Again, yt is change of this x, right? This change of x. Suppose x is Samsung Electronics and SK Hynix. YT is the factor of change of Samsung Electronics price and change of SK Hynix price. And somehow change of Samsung Electronics price and change of SK Hynix price depends on the level of SK Hynix or Samsung Electronics. It means that we can predict the change, right? And then we make profit. Change of stock return, change of stock price. Therefore, we can make some possible profit. Depends on level or the gap between the two, right? Or linear combination between the two. So testing for co-integration is easy, whether they share common factor or not. Fit the model in equation 1. Where is equation 1? Yes, this one. We fit the model. We estimate this model. And then test for rank of this one. We estimate this one, the rank. If xt is k-dimensional and rank phi is m, then we have a k minus m has a unit root. We have a k minus m unit root. There are multiple unit roots. Okay. So if it is not, there is no unit root, this rank should be 0, which means that this one, all elements should be 0. Rank means number of independent vectors in this matrix. Pi, phi. Now there are m linear combination of xt that are unitless stationary, which means, right, because this is k dimensional and k minus m unitless. K minus m, they are interrelated, co-integrated, so we have m linear combination stationary. If now this pi have rank m, only m independent vector, then we can rewrite, it is simple linear algebra, we can rewrite this pi as alpha beta. Okay, this pi as alpha beta, where alpha is k multiplied by m multiplied by k, where alpha and beta has a full rank, which means that their rank is m. Okay, zt is beta xt is unitless stationary process. Okay, this is important. Here beta the co-integration. This is called co-integrating vector. Discussion. Error correction model formula is helpful, useful, and the co-integration tests some weakness like robustness, and the co-integration overlook the effect of scale of the series. In R, the package URCA of R can be used to perform co-integration tests. Pair trading, reference pair trading, quantitative method analysis by Kanapati Vidyamuthi, Wiley 2004. Motivation. General idea of trading, pair trading, is to sell overvalued securities and buy undervalued ones. But the true value of the security is hard to determine in practice. We may not know true value of Samsung Electronics and true value of SK Hynix. Pair trading attempt to resolve this difficulty by using relative pricing. Even though we do not know true value of Samsung Electronics and true value of SK Hynix, maybe the ratio between the two, stock price ratio of two stock price, maybe we know something about it. Basically, if two securities have, and we want to exploit that intuition, relative pricing, for pair trading. That's the idea. So basically, if two securities have similar characteristics, then price of both securities must be more or less the same. Here the true price is maybe not important to make money. In statistical term, the prices behave like a random walk process, but the linear combination of them is possibly stationary. Hence, the linear combination mean reverting stationary. Okay, deviating from the mean leads to possibly trading opportunities. Theory in finance, that is deeply related to theory in finance, it is arbitrary pricing theory. If two securities have exactly the same risk factor exposure, then the expected return of two securities for a given time period are the same. The key is that the return must be same for all time. More detail, consider two stocks, stock 1 and stock 2. Let PIT be the log price of stock I, T. It is reasonable to assume that the time series of P1T, log price of first one, and P2T, log price of the second stock, contain the unit when they are analyzed individually. Okay? But assume that two log prices are co-integrated. There's some relationship between their relative pricing. That is, there is a linear combination of C1 P12 and C2 P2T that is possibly stationary. Okay, even though we don't know individually this one and this one, linear combination is stationary, then it means that if we have enough data, we can estimate this one. We can estimate and predict what's going to happen between the gap between the two. Dividing the linear combination by C1, we have this one, which is stationary. The stationarity implies that WT, okay, this one, is mean reverting. Now, how can make money? We can form a portfolio Z by buying one share of stock 1 and selling short gamma share of stock 2. The return of the portfolio given period H is looks like this, right? Something like this. WT plus H. So if it is time, this WT plus is stationary, we can, if we have enough data, we can predict this, right? Then which means we can make money. Which is the increment of stationary is WT from T to T plus H. Since WT is stationary, we have obtained a direct link of portfolio to stationary times whose forecast we can predict. We can predict the future, then we can make money. A trading strategy: buy stock 1 and short gamma share stock 2 when WT equal gamma minus delta. Unwind the position if sell stock or sell stock 1 and buy gamma share stock 2 when this one is. So basically, this delta thing minus plus delta is in some sense threshold. When the gap between the two log prices deviate from this gap, we trade. Some practical consideration: the threshold delta is chosen so that the profit outweighs the cost of trading. In high frequency, delta must be greater than trading slippage, which is the same linear combination of bid-ask spread of two stocks, i.e. bid-ask spread stock 1 plus gamma bid-ask spread stock 2. Here, slippage, this is trading slippage, important. Trading slippage means that when we trade some stock, because we send orders to trade stock, it affects supply and demand, so price may move undesirable way. That incur cost of trading, and which is called trading slippage. Speed of mean reverting or WT plays an important role as H is directly related to the speed of mean reverting. There are many ways available to search for co-integrated pair of stock, for example via fundamentals or risk factor. For unit and co-integrated test, see the textbook reference thereof. Okay? Example. Consider the daily adjusted closing stock price of BHP Billiton Limited Australia and Vale SF Brazil. Both of them are input mining companies, energy mining and energy companies. Okay, these are two natural resource companies, world-leading natural resources companies. Both stocks are also listed in New York Stock Exchange with tech symbol BHP and Vale, respectively. The sample period is this one. Now we want to estimate gamma. Gamma is like a portfolio weight and speed of mean reverting. Okay, so this is sample code. Okay, long. Okay. So let's do some simulation. Here again we could call close. Okay, next generate co-integrated vector to co-integrated time series and then save it as Excel file. Visualize the co-integrating relationship. Okay, certainly this one. Wow, it even performed Johansson co-integration test. Okay, so let's copy. Okay, let's see. This is, I love this generative AI. They are so good. Okay, so paste and then run it. Okay, it generates two co-integrated series, but they doesn't look possibly well. They move the other way. Actually, the other way around is also co-integrate. The co-integrated beta co-integration relation is something like this. Okay, this looks stable. Okay, so actually if we increase number of data here, um, what if we increase more data? Okay, okay, 10,000, 10,000. Okay, then this correlation process is actually, well, this is more like move around the zero. Okay, so let's see the, now we reduce the data. Okay, let's read from the beginning. So import numpy, import pandas, import matplotlib library, and stat methods. Now factor VCM, factor correction model, and co-integration Johansson co-integration test. Okay, number of seed 42. Right, let's reduce it again for make it quick. 1,000 samples. E1 now NP random variable 1, 0, and n. Okay, 1,000, and this is random variable. And then y1 is number of cumulative sum of epsilon 1 and cumulative. So it means that there is a here there is a, they are both of them, they both of them are unit root, right? There is a sum of random variable, cumulative sum. Now we create a co-integrated series. So beta is 0, 1. So z is y2 minus beta. So this beta is co-integrating vector. Now we can add some noise to make it more realistic. So y2 is y2 plus 0.0 and random number. Now we create, this is not, this is not correct basically. No, they are not co-integrated. So sometimes, well, this is wrong. Um, yeah, this is clearly wrong. Yeah, they are not co-integrated. They are not co-integrated here because we are simulating y model. They share z. Okay, so both of them should be subject to z. Okay, so, well, this is wrong. Okay, you are wrong in the code. y1 and yt2 are not co-integrated. Okay, they are not co-integrated. Okay, so again, yes, here beta 2 is beta y1. Okay, so cum sum, now it seems, now it looks better. Okay, so let's copy and then delete this one, and again, okay, so there is error. So let's teach error to the cloud. Okay, let's see. I hope this works. Again error. Well, error again. Let me copy again. Copy and simply delete this one. Well, this is not difficult. Why they make mistake? Here y2 is beta. Here beta is 0.8, and then we add y1 plus and become sum e2 error correction term. Okay, let me change it. Instead of error correction model, what we can do is, okay, y1 cum sum, this one, and then this is not rigorous. Yeah, let me directly change it slightly. So let's use some temporary variable here, like this. Then we have this one, and then we have, well, we can add error term over here. Okay, over here, and then I define y1 as y, yeah, e2, but instead of this one I can add another error term. Okay, well, uh, well, in me then there is no correlation between the two, but well, it is fine by now. And let's run. Now data frame, create the data frame y1, then I can use this one. Okay, so we don't need this one, and then now it seems working. Okay, so wow, they are too correlated. Well, they are too correlated. I may have to add more error. Clearly, and trace estimate critical value 99 is, so they are highly critical. Okay, trace statistic. Well, they are too correlated in some sense. Co-integrated relative to all move look quite stationary. All move around zero. Co-integrated relation. So, well, I successfully generated it. So okay, so let me ask again. Okay, where is the, I think this code is the right approach. Okay, so I teach ChatGPT what is right. You are absolutely right. I approach you provide the improved approach. This could indeed a better way to capture. Okay. Okay. Next, update, generalize my code to look like a more realistic time series. Okay, and then I give code, I give hint to ChatGPT, I give Claude, and then want to generalize. Okay, so then yes, it does generalize. Okay, nice. Okay, okay, so let's now copy the code and let's run run the code now, which is based on my code. Then run. Okay, let's see line by line whether they are right. Okay, so well, this one seasonal. It now the seasonal decompose. Okay, interesting. So again, 1000 TNP orange and time component. Wow, it add time component. Okay, now drift 0.05. Now E1 is MP random and Y1 is MP cum sum drift plus E1. Okay, now we add drift term, and every period, okay, we add 0.05 trend. So there is a trend, add trend and seasonal to Y1. Okay, so we trend 0.01 T, and then where seasonality, we again add seasonality. Interesting sine function. So y1 bar is previous y1 bar plus trend 1 and seasonality. Okay, we add trend and seasonality. Now create cointegrant time series. Again, beta is 0.8, E2 is normal, and add a different trend and seasonal to y2. Trend 2 is now 0.015t, increase over time. Seasonality is now cosine of this one. Okay, so y2 is beta y1, this one, and the trend and seasonality and normal variable. Okay, and add noise to y1 underbar. Okay, something like this. Okay, now add some auto regressive component. This is another, yeah, good idea, very good idea. Okay, now ChatGPT works by auto regressive relationship. So y1 is this one, and then yeah, something like this. Yeah, so this one is affected by its own leg and then previous leg. This one is affected by its leg, and so yeah, this is there's a co factor autoregression relationship. I'm very happy about this one. Now create a data frame. Okay, with the data range, this one, and then yeah, period. It even assigned the date. Even assigned the date. Very good. Okay, and then wow, it name, and then this one, realistic coincident time series. Okay, which is this one. Okay, realistic coincident time series. You can download this data and look at how they look like, and the plot realistic cointegrated time series, cointegrated relationship. Now plot the seasonal component of y1. Okay, seasonal decomposition, seasonal decompose, and this one. Okay, perform Johansson co-integration test. Good. Okay, so now realistic cointegrated, there are two cointegrated time series. Okay, cointegrated time series, and then cointegrated relation between the two. Okay, cointegrated relationship is again, even this co-integration series is not stationary because there is not stationary because there are time trend, and then there is seasonality. So seasonal component y1 for 100 observation, something like this, and then we trace and critical value all greater than 0. 0 is not included, so all significant. Okay, great. Next, 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 next. Interesting. Next, upload the simulated Excel file, which is realistic co-integrated one. Excel file, and then estimate the process with factor error correction model. Okay, let's see whether we can do. Okay, td print data head. Nice, it is even better than ChatGPT. Loaded co-integration time series, and then max rex 5 factor error correction model, result lag, and then best model, we pick the best model and print the co-integrating vector, forecast horizon. Wow, this is amazing. Okay, this is amazing. This is rich code. Okay, so let's copy the code, and then okay, then let's run it. This is very rich and very nice code. Once I give hint to AI, it just does such a wonderful work. Okay, so okay, let's. Wow, this is pretty long output. Okay, long output. It is not wonder. Okay, so because it did a lot of tests. Okay, so first we read the Excel file, realistic co-integrated trees, index column data, and then check the first few row of the model, printed df head. So data. Okay, so data look like this one. Date and then y1, y2. So this is data. And then yeah, plot the time series. Okay, PLT figure and then 1, 2. Okay, we stack each other, loaded co-integrated time series, and this is loaded co-integrated time series. They are clearly, visually, vividly co-integrated, and then they have clear time trend. And then next, estimate factorial correction model. We will try different lag orders and co-integrated ranks. Max lag 5. So, well, because we only have this data, therefore, well, by just looking at the data, we don't know the lag. Of course, we simulate with lag length 1, but we don't know, okay? We don't know within the data. So we do the test. So in range 3, R is co-integration rank. So model DFK are different. K is the co-integration rank, and then co-integral rank again. K is y. K is this one until max x plus 1, and then co-integral rank is, well, it can be 1 to 3. So actually it's a run combination. Try result model fit result KR. Okay, rank result summary. Could not find the factor according to KR. Okay, so let's take the print. Wow, this is so long print. So first leg 1, the VSM result. So when leg 1 rank 1, it could not find the factor according to rank 0. And when it does try rank 1 rank 1, which is indeed the true model in our case, okay, the terms outside the co-integral relation lagged endogenous parameter is that, okay, so, well, coefficient is, well, they are significant is that one is this one, okay, this one, and standard error, so this is significant and this is not significant. And then yeah, L1 Y1 looks like this, and loading coefficient alpha for equation, okay, then it is this one, okay, and error correction part is 0.28, okay, and then co-integration relation is 1 1 and then, well, -1, okay, so roughly fine, okay. True co-integrating factor correlated to 0.8, but yeah, uh, how about we use rank 1 rank 2, okay. Rank 2 is, yes, if we take a look at it, rank 1 1, okay, loading coefficient to alpha for equation 1. So 0 0, okay, so we have rank 2 rank 0 not find, okay, so we keep trying this one, okay, keep trying this one, and then if we do this one, okay, after estimated, let's use the model with the best fit, okay. best model is VCMTF KR different to, okay, 2.1 and deterministic part, and best is the model fit, okay, so best model, and print co-integrating vector best model best result. So here this is, wow, this is too much result, so well, we here we let's, for temporarily let's hide this print part. If we print part, okay, okay, we have to print result summary, then it is too long. This is too long, so okay, anyway, well, let's reduce, okay, this is too long, okay, this is simply too long, so instead of max rec 5, max rec 1, okay, let's 1, okay, max rec 1, then we can show it does show the one result, okay, good. Co-integral relation of beta 1 to co-integral relation for loading coefficient, co-integrating factor is this one. So original forecast, well, they are pretty overlap each other, okay, pretty good. Here in our simulation, co-integrating vector is 0.8, right? But I think if we increase the size of data, then we will have a better result. But anyway, I think this is reasonable enough. They perfectly match the data, okay? Forecast. Okay, this is confusing, so to integrate result, to interpret the result, let's take a look at only this part again. Only this part again, and then, yeah, it's too long. We want to interpret the result, so, well, here, let's do only do this part again. Okay, best model, best result fit. So we have a co-integrating vector. Okay, so actually we want to see the result as well. Okay, so best result summary. Okay, summary. Okay, and then print. Okay, summary. Okay, best model fit summary, best result beta, co-integrating vector 1. Okay, so this is best result. So, well, we know our true model is, it has two legs, so we have a constant term for y1, we have this one and this one, second leg, and then for constant term first leg and then second leg. Now loading coefficient for alpha, and then loading coefficient alpha for equation 2 is like this, and then co-integral relation. Okay, so this is interesting part, so let's okay, let's copy. Okay, so okay, so explain this part mathematically. Okay, mathematically, this output represent vector error correction model with co-integrating relation. Let's break down mathematically. The general form of vector error correction model with one co-integrating relationship, in our case one co-integrating relationship, it has change of yt, okay, is alpha beta yt minus 1, okay, alpha beta, okay, alpha beta part is exactly alpha beta part is exactly equal up and up, okay, alpha beta, okay, yeah, this one, this alpha beta, okay, exactly this one. And then this is gamma 1 and gamma 2. We estimate gamma 1 and gamma 2 second leg. So y is the factor of variables. Actually, there is the first difference order change. Now alpha is a factor of is called adjustment coefficient, loading coefficient. Beta is called co-integrating vector. Okay, this is matrix of short-term coefficient. Epsilon is the factor of error term. Now loading coefficient alpha for y1 is this and y2 is this one. So if we take a look at the result, okay, yes, here, okay, this is first one is minus 0.1433 minus 0.0046. So yeah, 1.046. Not they are not statistically significant though. Okay, co-integrating vector 1 and then, well, the correct one is 0.8, but yes, this one and this one is, well, the co-integrating vector is very statistically significant. Okay, the correct one is 0.8 though. We write our vector error correction equation as this one is alpha 1 of beta 1 beta 2 this one and beta 1 beta 2 this one. Okay, so this is error correction part. Beta 1 is here, 1, beta 2 is this one. Okay, error correction part. So, well, so this linear relation between the two part. Okay, so substituting the value, this one is, yeah, 0.1433 and then co-integrating relationship and then minus this one and this one. So basically this means that whenever there is a deviation between the two co-integrating relationship, the first one, okay, first one respond by this one. So suppose the first one is Samsung Electronics, the second one is SK Hynix. Well, this is, they have like one, they are all log basically. We use log. So log price of Samsung Electronics and log price of SK Hynix. Well, we can form the portfolio by taking long position of Samsung Electronics and short position almost one, but 0.97 amount of SK Hynix short position, and then we can combine them in the portfolio. When the value of portfolio change by 1, Samsung Electronics drop by this amount and SK Hynix drop by this amount. Okay, this is the intuition. Okay, so when there is a change, Samsung drops more, right? Drops more than this one. So when this goes up, we have to sell the first one, Samsung, and then buy SK Hynix, something like that. Okay, the term in parentheses, this one represents the error correction term, which is very co-integrated relationship, which we call ECT1. So we can write our equation with ECT1, ECT2. Actually, this is what the result shows. Yes, ECT1, EC1 here, actually ECT1. Okay. So interpretation is the co-integrated relationship suggests that in the long run, y1t is approximately same to 0.97, although the correct one is 0.8. If we increase sample size, then this number should converge to, will be very similar to 0.8, I'm pretty sure. This is the equilibrium relation between y1 and y2. And for y1, if the system is above equilibrium, like the equilibrium, then y will decrease in the next period. Below equilibrium, increase. So the adjustment speed is 40.33%. Okay, yeah, of the disequilibrium per period. For y2, the adjustment coefficient is very small. Virtually does not move basically, and not statistically significant. P-value is very high. This suggests that y2 doesn't significantly adjust to correct disequilibrium in the short run. The co-integrating factor is 1 and minus 0.97 implies a 1 unit increase in y2 is associated with 0.974 unit increase in y1 in the long run. This mathematical representation helps us understand the long-run relationship between y1 and y2 as well as how y1 adjusts to maintain this relation in the short run. Perfect explanation. Okay, the result suggests that y1 does not most of the adjust. Y1 does most of the adjustment to maintain long-run equilibrium, while y2 appears to be weakly exogenous in this system. Okay, very nice explanation. I love this cloth. Okay.